1:23 a.m. on April 26, 1986. Inside Reactor 4 at the Chernobyl nuclear power plant in Soviet Ukraine, operators pressed the emergency shutdown button. Seconds later, Reactor 4 exploded. The system had been designed to shut itself down safely. Instead, the final safety command became the trigger. When you open the archives of human history to examine its most devastating failures, you discover events that defy logic. Cases where the exact systems built to protect us become the very things that destroy us. Welcome to Uncatalogued. Today, we are looking at a catastrophe that didn't just break a machine, it poisoned a continent. This is the story of Chernobyl and the 1:23 a.m. test. Hours earlier, the reactor was not supposed to be proving anything dangerous. It was scheduled to conduct a turbine rundown test, a safety verification. Engineers wanted to know if the spinning turbine could generate enough leftover electricity to power cooling pumps during a sudden blackout, just until the backup diesel generators kicked in. To simulate this, the reactor had to be brought down to low power. But an RBMK reactor does not behave predictably at low power. As the power drops, a chemical byproduct called xenon builds up inside the fuel channels. Xenon acts exactly like a sponge, absorbing the neutrons that keep the nuclear chain reaction alive. The more xenon builds up, the more it chokes the reactor. Power falls further, xenon increases, and the choking effect compounds. By the time the night shift took over to stabilize the test, the power had collapsed way below the safe level. The reactor was barely breathing. To force the power back up, operators started pulling out the control rods. Control rods are the reactor's brakes. Push them in, the reaction slows down. Pull them out, it speeds up. But the xenon sponge was still aggressively eating the neutrons. So they pulled out more rods, and then more. The reactor was now pushed completely outside its safe operating limits. Almost no control rods were left inside. To stop the automatic safety systems from shutting down their test, they intentionally bypassed the alarms. The physical safeguards were gone, while internal instability was climbing. At normal power, the high-speed water flowing through the reactor actually helps dampen the nuclear reaction. But at low power, the physics invert. When water turns to steam, it stops absorbing neutrons. Less liquid water meant more nuclear reaction. Shortly after 1:23 a.m., the turbine test began. Steam to the turbine was shut off. As the turbine slowed down, electrical output to the cooling pumps dropped, and water flow through the core began to fall. Less water meant more boiling. More boiling created pockets of steam. And in this specific reactor, steam increased the reaction. Control room instruments didn't immediately show the danger. The readings appeared manageable, but deep inside the core, instability was violently building. Boiling intensified. Steam pockets multiplied. Reactivity accelerated. 1:23 and 40 seconds a.m. Operators pressed AZ5. This was the emergency shutdown, the ultimate failsafe. It ordered all control rods to drop fully into the core designed to kill the reaction instantly. The rods began to fall, but these rods had a fatal design flaw. While the main body of the rod was made of boron, which stops the reaction, the very tips were made of graphite, and graphite accelerates it. For a fraction of a second, those graphite tips entered the core first. In a stable reactor, this brief power spike would be harmless. But in this severely crippled, unstable configuration, it acted like a match in a powder keg. Power surged locally. Fuel channels instantly overheated. The water flashed into steam in a fraction of a second. Pressure violently deformed the internal structures. The control rods jammed partway down. The braking system was physically destroyed. Power didn't double. It multiplied. Within seconds, energy output skyrocketed. Steam pressure lifted the 2,000-ton steel and concrete shield, resting directly above the core. A violent explosion tore through the reactor vessel. The core was exposed to open air. A second explosion followed immediately after. Inside the control room, operators faced dead panels. Many believed the reactor had simply shut down. The idea that the core itself was gone was completely outside their training. Firefighters arrived within minutes. They climbed onto the roof to fight what they thought was a normal chemical fire. They had standard helmets and water hoses. No radiation suits. No dosimeters. They walked among glowing fragments of graphite and reactor fuel, handling them directly. They absorbed lethal doses of radiation in minutes. Acute radiation sickness isn't like a burn or a broken bone. It begins at the cellular level. Bone marrow fails. The immune system collapses. The injuries were invisible at first glance, but catastrophic beneath the surface. Outside the plant, the city of Pripyat woke up and continued normally for critical hours. Evacuation was delayed. Meanwhile, the reactor continued to burn. Helicopters dropped sand and led into the open crater, desperately trying to regain control of a system that no longer existed. What failed that night was not a single action. It was a deadly interaction between design and procedure. A reactor unstable at low power, a physics flaw that amplified boiling, control rods that briefly increased the fire before putting it out, and safety systems manually disabled. Each factor alone was manageable. Together, they formed a devastating, reinforcing loop. At 1:23 a.m., the shutdown button was pressed to regain control. But by then, Reactor 4 was no longer a machine. It was a system amplifying itself. And once amplification begins inside an unstable design, it does not reverse gently. Chernobyl proved that the most devastating threats aren't always the disasters we fail to predict. Sometimes they are the very fail-safes we build to stop them. This file is now closed, but the archives are deep. Subscribe to Uncatalogued, and we will open the next one together.